in Pharmaceuticals in association with Higher Secondary Principals Forum.
Hello students, today we would be continuing with chemical kinetics. In part 1 of the chapter, we have already covered what is rate of a reaction. We have seen how to write down rate of a reaction in terms of reactant and product concentration. We have also seen what is differential form of the rate equation. We have seen what is the type of reaction rates, average and instantaneous. We are familiar now with what is order of a reaction, what is molecularity of a reaction, and we have also derived integrated rate equations for 0 and first order reactions. Besides this, we have also seen what is half-life of a reaction and how to derive half-life for 0 and first order reactions. Now, in this part of the chapter, we would be focusing basically on the other two factors that influence rate of a reaction. Concentration, which we have already done in part 1. In this part, we are going to look at how temperature influences rate of a reaction and the presence of a catalyst, how it influences the rate of a reaction. Now, before we start with that, we would see what are the different units of rate constant, because the unit of rate constant depends upon the order of a reaction, whether it's first order, 0 order or any whatever is the order. But the rate of a reaction doesn't depend upon order of a reaction. Rate of a reaction has the units as moles per liter per second. The unit of rate constant for a reaction that is given here, A plus B giving you C plus D. Now, the small a, B, C and D are going to be the number of moles of the reactant and the product. The rate expression is given as K into A raised to X and B raised to Y. We know that X and Y is supposed to be the order of the reaction. The sum of these powers would give the order of the reaction. So, the rate constant K, if you keep it on one side and get the concentration terms on the other side, would be equal to rate upon the concentration of the reactants, which would be equal to rate has the unit of concentration upon time, which we have already said that rate has a unit of moles per liter per second. And the rate constant would be rate, unit of rate divided by the concentration. Concentration of the reactant, here N would refer to the order. Suppose it's a 0 order reaction, then you're going to substitute the value of N as 0. If it's first order, you're going to substitute the value of N as 1. So, it depends upon the order of the reaction. Here in the table, you can see that if the reaction is of 0 order, the unit is just going to be moles per liter per second, because here you would have to substitute the value of N as 0 and anything raised to 0 is going to be 1. In that case, rate constant would have the same units as the rate of the reaction, that will be moles per liter per second. For first order reaction, we find that the unit is second inverse. Now, why it is second inverse is because you would have to take the concentration here N value as 1 and the concentration would be measured in terms of moles per liter. Here you would have moles per liter, you would have moles per liter and moles per liter getting cancelled. And finally, you would have 1 upon time, and if time is measured in seconds, then the unit is going to be second inverse. For a second order reaction, again what we have to do is in this equation substitute the value of concentration as 2. So, moles per liter square it's going to be. So, if you have to consider now K, the unit rate of unit of rate is mole per liter per second. The unit of concentration is going to be mole per liter per second into again moles per liter into moles per liter. This is the unit of concentration. Now, why have I multiplied it 2 times? Because we are going to take the value of N as 2 here. That's the reason we are going to multiply here moles per liter twice. The final unit is going to be second inverse will remain, and a mole which is in the denominator when it comes in the numerator becomes mole inverse, and liter inverse will be liters. So, the unit is mole inverse liter second inverse, as you can see it here in the table, mole inverse liter second inverse. So, that is going to be the unit for a second order reaction. So, whatever is the order of the reaction, you just have to use the same equation, replace the value of n as 0, 1, 2 and whatever the order is, and find out what is going to be the unit. So, it is the same equation that you are going to use to find out the order of the rate constant. So, you need to remember that the rate constant does not have a specific unit, it depends upon the order of the reaction. Now, what we are going to discuss is what is pseudo first order reaction. Now, these reactions appear to follow second order kinetics, but actually follow the first order kinetics. Now, why do we say so? Suppose I have a reaction here of ethyl acetate reacting with water. As I have mentioned, it is an excess giving ethanol and ethanoic acid. Now, in this expression, if no other information was given to you, you would write down the rate law expression as rate is equal to K dash, I have just written K dash as the rate constant, into concentration of acetic acid into concentration of water. Now, since 1 mole of acetic acid is reacting with 1 mole of water, we would raise these concentration terms by 1 and 1, which I have not written because it has to be assumed that it is 1 when it is not written. Now, the concentration of water is taken as a constant. The reason is because in this reaction water is taken in excess. So, the overall rate will not depend upon the change in the concentration of water because it is taken in excess. It would depend upon the change in the concentration of ethyl acetate. So, if you take the concentration of water as a constant, suppose it was taken as 10 moles water or concentration of water, and a very little amount of ethyl acetate is taken, 0.1 moles. Out of 10 moles, you would have only 0.1 mole of water reacting with ethyl acetate if you have taken 0.1 mole of ethyl acetate. So, you have still considerable amount of water remaining in the reaction mixture. That is the reason we find that the concentration of water does not alter much in the reaction as it is taken in excess, and therefore, it is taken as a constant. So, the concentration of water and the rate constant together is given as K here, K dash into water, which is a new constant now, into the concentration of ethyl acetate. So, the rate is equal to K into concentration of ethyl acetate. Now, if you look at the order, if I have to tell you that this is the rate expression, and if I have to ask you what is the order of the reaction, you would say it is a first order reaction because there is just one reactant here and it is raised to 1. But if you look at this rate expression, there are 2 reactants, each of which is raised to 1, the order would be 2, alright. So, pseudo first order reactions are those which show to behave as if they are following second order kinetics, but actually they are following first order kinetics. They are made to behave like first order reactions, alright. So, you need to remember which are pseudo first order reactions. Any reaction which could have any one of the reactant or 2 of the reactants in excess, or if the concentration of the reactant does not change, that means it does not affect the rate of the reaction, such reactions normally come under pseudo first order reactions. The second factor that we are going to study today is how temperature affects rate of a reaction. We have already seen how concentration affects rate of a reaction. Now, for temperature, whenever we carry out reactions at very low temperatures, we find that the reaction is sluggish. It takes place at a very slow rate. But as soon as the temperatures increase, we find that the reaction rate also increases. So, we see that rate of a reaction increases with increase in temperature. Now, you should not confuse this with enthalpy of reaction. Enthalpy is different altogether. Enthalpy is going to be the change in the energy of the reactant and the product. Finally, when you get the reactant and the product, the change in the energies of the reactant and product is enthalpy. So, you could have reactions which are exothermic, you could have reactions which are endothermic. Now, enthalpy, if it is endothermic or exothermic, that would affect the yield of the product. That means, if you are going to get say 50% of the product at a particular temperature and increasing the temperature decreases it to 30%, then that affects the yield, that is how much of the product you are going to get at the end of the reaction, or where the equilibrium is going to lie. Here in this chapter we are interested in how fast you can attain equilibrium, alright. So temperature helps to attain the equilibrium faster. Increasing the temperature increases the rate of the reaction. Now for a chemical reaction, this is noted that with rise in 10 degrees, the rate constant nearly doubles, alright. So you need to understand that every time temperature increases, the rate of the reaction increases, the reaction becomes faster. Arrhenius has used this equation for us to understand the use of temperature, how it affects the rate of a reaction. Now we don't need to know the derivation of this equation, we just need to know what the equation is and what the terms are that are involved in the equation. K is equal to A e raised to minus EA upon RT. K is the rate constant, A is known as the Arrhenius factor or the frequency factor, EA is activation energy, and T is going to be the temperature in Kelvin. R we have already studied in standard 11 is also known as universal gas constant, which has a value of 8.314 joule per Kelvin per mole. Now here what is new to us is EA, the activation energy. We have to understand what is the meaning of activation energy. According to Arrhenius theory, before giving this equation, there is a theory. In this theory, reactant molecules are supposed to react. They are going to have some amount of kinetic energy associated with them. They collide. They form something known as the intermediate or an activated complex. Now this complex cannot be isolated. It is a hypothetical complex and it's supposed to have very high energy. Once the activated complex is formed, quickly the activated complex, since it's unstable, it's going to disintegrate and form products. Alright. So in this theory we have reactants reacting to give you activated complex and the activated complex disintegrating to give you products. Now if you look at this plot here of potential energy versus reaction coordinates, you have the reactants hydrogen and iodine giving you products hydrogen iodide. Hydrogen and iodine is marked as A, which has some amount of potential energy. Hydrogen iodide is marked as B, which again has energy less than the reactant A. As you can see, the difference in both these energies of the reactant and the product is given as delta H, which is known as enthalpy of a reaction. Enthalpy helps us to find out whether a reaction is endothermic or exothermic. And as I said, in Arrhenius theory, we have the reactants reacting to give you an activated complex which has very high energy, which can be shown by C here in the graph. And quickly the activated complex, when it is formed, it disintegrates to give you products. Alright. Now the difference in energy between the reactant and the activated complex is known as activation energy. Alright. This is important to us because in the previous equation we had a term called EA and we said that it is activation energy. The meaning of activation energy is here, the difference in energy between the reactant and the activated complex. Again, let me repeat that the activated complex is hypothetical, it cannot be isolated from the reaction mixture. So whenever the activated complex is formed, there are bond breaking and bond forming processes taking place simultaneously. So the entire rate of the reaction actually depends upon how quickly the activated complex is formed. If the energy difference, the activation energy is very high, then the reaction is going to take a very long time, like rusting of iron. We can expect that the activation energy is very high because it's a very slow process. So this activation energy will be high for the rusting of iron. As soon as the activated complex is formed, the products are going to be formed quickly because activated complex has very high energy and it is unstable. So it disintegrates quickly and it gives you the products. So the overall rate of the reaction, remember, depends upon how quickly the reactant forms the activated complex according to Arrhenius theory. Now we have to look at how temperature affects the rate of a reaction. That is, why do we say that whenever you increase the temperature, the rate of the reaction increases? Here we have a plot of fraction of molecules versus kinetic energy. The meaning of fraction of molecules would be, suppose you have 2 molecules out of 10 molecules or 2 molecules out of 100 molecules. The fraction is going to be 0.2 of 2 upon 100. Now, if you look at this curve here, the number of molecules having very low kinetic energy, the fraction of molecules having very low kinetic energy is very less here, the area under the curve, while again the fraction of molecules having very high kinetic energy is also very less. The most probable kinetic energy is here in the middle of the graph. Most of the molecules have kinetic energy which is going to be somewhere here in between the lowest and the highest. Suppose we say that the reacted molecules have 5 kilojoule per mole of energy. The meaning of this is 5 kilojoule is going to be the most probable kinetic energy. Alright. So, it is not that all the reactant molecules present in the reaction mixture will have 5 kilojoules per mole of energy. It could also mean that some of the reaction molecules will have very low energy, could be even 1 or 2, and some could be having a little higher energy, suppose 10 or 12. But most of the molecules have on an average of 5 kilojoules per mole of energy, and that is represented here in the plot. That is the most probable kinetic energy. So, this is going to be a graph for any reactant having some amount of energy at a particular temperature. Now, how this plot changes when temperature increases is what is going to be important for us. So, here if you look at the graph at a higher temperature, the number of molecules having energy greater than the activation energy is greater compared to the graph which is at a lower temperature. So, the blue portion of the graph here represents molecules which have energy greater than the activation energy, while the red portion of the graph shows the molecules having energy greater than the activation energy is higher compared to lower temperatures. So, what temperature does is it increases the number of molecules having energy greater than the activation energy. In that case, the reactant molecules will form the activated complex easily, and then it will form the products. Now, what you have to remember here is there is nothing that is happening to the activation energy. The activation energy does not change. It is the same at higher temperatures as well as at lower temperatures. Only the fraction of molecules having energy greater than the activation energy increases. So, according to the Arrhenius equation that we had seen earlier, which is K is equal to A e raised to minus EA upon RT. If you have to take natural logs here, it becomes ln of K is equal to minus EA upon RT plus ln of A. A here is known as the Arrhenius factor, or it is a factor which is going to be constant for a particular reaction. Alright. Now, at two different temperatures, the equation gets modified as log of K2 upon K1 is equal to EA upon 2.303 R into T2 minus T1 upon T2 into T1. Now, what you need to understand here is this equation is important with respect to solving numericals. You could be given two different rate constants at two different temperatures. So, you should be able to solve numericals when such type of problems are given. The derivation of this final equation is not there for you. You just need to know the final equation and use it for numericals. Alright. Now, if you look at the graph here, it is a plot of ln of K versus temperature 1 upon T. So, this equation is of the type y is equal to mx plus c. Y is going to be ln of K, c is going to be the intercept here ln of A, and 1 upon T is on the x axis. The slope is going to be minus EA upon R. Alright. So, that is going to be the slope of the line. So, you should be able to plot the graph. You should know what to write on the x and the y axis, the slope as well as the intercept, using this equation which we have taken from the above equation. Now, next factor which affects rate of a reaction is the presence of a catalyst. Now, what is the need of a catalyst? A catalyst helps in increasing the rate of the reaction. What it does is it alters the activation energy. Temperature does not change the activation energy, but catalyst alters the activation energy. It tries to reduce the activation energy so that the reaction takes place faster. So, a catalyst is added to a reaction mixture wherein it changes the reaction pathway and changes the activation energy, leading to the formation of product. At the end of the reaction, you get the catalyst back, it is regenerated. It is not used up in the reaction, it just helps to change the mechanism of the reaction. So, a catalyst is a substance which alters the rate of a reaction without itself undergoing any permanent chemical change. That is what I meant by saying that at the end of the reaction, the catalyst can be recovered. It provides an alternate pathway or reaction mechanism by reducing the activation energy. I have already discussed this point. Then lower the value of activation energy, faster will be the rate of the reaction. That is how a catalyst affects the rate of the reaction, it lowers the activation energy. Then a very small amount of the catalyst is enough to carry out a reaction. You do not have to add a lot of the catalyst because it can alter the reaction mechanism even when it is in small quantities. And another important thing is that a catalyst only affects the rate of a reaction. It does not change a non-spontaneous reaction to a spontaneous reaction. That means it does not affect Gibbs energy. So, a reaction which does not take place on its own, adding a catalyst will not help for the reaction to take place on its own. And also it does not affect the equilibrium constant. Equilibrium constant helps in attaining more amount of products. That is, if the value of Kc is high, we say that we get more amount of products. The yield of the reaction is going to be high. So, a catalyst does not increase the yield of a reaction. A catalyst only helps to attain the equilibrium faster. It does not increase the amount of the products. So, here we have a plot of potential energy versus reaction coordinates. In this plot, we can see that the reactants have some amount of energy, products are going to have some amount of energy lesser than the reactant. The difference of this energy is going to be delta H. There are two plots here. The first plot is showing activation energy here. It is carried out without the presence of any catalyst, and you can see that the activation energy is high here. The second plot, which is represented by these dotted lines, that shows the same reaction being carried out with the presence of a catalyst. So, as you can see the difference, the activation energy which was here earlier has reduced. So, this is the new activation energy with the presence of a catalyst. So, that is what a catalyst does. It reduces the activation energy and hence it increases the rate of the reaction. Now, the last part of the chapter is to understand something known as collision theory. We have seen what is Arrhenius theory and how temperature affects the rate of reaction. According to collision theory, this is also based on Arrhenius theory, but there is another factor that we need to introduce in collision theory. According to this theory, the reactant molecules are considered to be hard spheres, which are at constant collision with each other. So, they keep colliding with each other. These colliding molecules need to have some specific amount of kinetic energy and they should have something known as proper orientation. Alright. So, in this theory, the molecules which have effectively collided are the ones that are going to result to the formation of products. So, what are the conditions that are needed for effective collisions? Effective collisions will take place only if sufficient amount of kinetic energy is available and with the reactants, and if the reactants are properly oriented. So, these are the two important requirements for effective collisions, and it is only the effective collisions that will lead to the formation of products, while other collisions will bounce back and form the reactants, will not form the products. The number of collisions that take place per unit volume of a reaction mixture is known as collision frequency. So, this is a term that is introduced because in collision theory the molecules are considered to collide with each other So, the amount of collisions that are taking place per unit volume per second, it is known as collision frequency. And here if you look at this equation, rate is equal to Z e raised to minus Ea upon RT. It is similar to Arrhenius equation except for the fact that Z is what is substituted here in place of A, which we had earlier, that was the Arrhenius factor. Alright. So, Z here represents the collision frequency of the reacting molecules, because we have introduced something known as collision frequency according to collision theory. Minus Ea upon RT here represents the fraction of molecules with energy equal or greater than the activation energy, because for effective collisions we need to have sufficient kinetic energy. Now, here in brackets I have mentioned threshold energy. What is the meaning of threshold energy? Threshold energy is going to be the energy of the reactant molecules. So, the energy of the reactant molecules, whatever is the potential energy of the reacting molecules, plus the activation energy. Alright. So, if this is the graph that you are considering, this is the plot that you are going to consider, the energy of the reactants and the energy, activation energy together will give you threshold energy. So, if the molecules have enough threshold energy, then they will lead to the formation of products. Another important point is proper orientation. Now, what is the meaning of proper orientation? This can be explained with the help of mechanism which is known as SN2 mechanism, which you have done in haloalkanes and haloarenes chapter. In that chapter we see how haloalkanes react with nucleophiles, and there are two different mechanisms, SN1 and SN2 mechanism. In SN1 mechanism we have basically two steps taking place, the reaction takes place in two steps. In SN2 mechanism the reaction just takes place in a single step. In SN2 mechanism we find that this is the alkyl halide, wherein you have bromine which acts as the leaving group, OH minus is the nucleophile which is supposed to attack carbon atom and lead to the loss of bromine, so that the final product that we get is an alcohol. So, it is just replacement of bromine with OH, this is the reaction. But how the mechanism for this reaction is that in between, these are the reactants, when the nucleophile attacks, if it attacks from the same side as that of the leaving group, if bromine is the leaving group, if the nucleophile attacks from the same side as that of bromine which is supposed to leave, then there is not going to be any products formed. For products to be formed, the reactant molecules have to be oriented properly. The meaning is the nucleophile which is there here, OH minus, has to attack from the opposite direction of the leaving group. So, if bromine is here, OH has to attack from the opposite direction. So, there is going to be simultaneously attacking of the nucleophile and the leaving group leaving the carbon atom taking place in this mechanism, and then you have the formation of methanol. So, this is the meaning of proper orientation, that is the reactant molecules have to be oriented properly for the reaction to take place, which could be best explained using SN2 mechanism. So, now the rate can be written according to collision theory as P Z e raised to minus Ea upon RT. This factor we have already discussed in the earlier slide, Z e raised to minus Ea upon RT. Z is nothing but the collision frequency, and P here is known as a steric factor, which is going to look at the orientation of the molecules. It is going to consider the orientation, whether the reactant molecules are properly oriented or no. So, it is going to take care of that, the value P, which is also known as steric factor. So, this equation explains collision theory as a whole, wherein effective collisions lead to the formation of products with the help of P and Z. So, in this chapter so far we have discussed, in the second part of the chapter we have discussed about units of rate constant. We have seen what are the different factors that affect rate of a reaction, specifically temperature, how it affects, and the presence of a catalyst, and finally we have seen what is collision theory. Now, you can be expected to solve problems based on the equations that were derived in the first part of this chapter, and also on equation that we have mentioned for temperature affecting rate of a reaction. wherein you can be asked to calculate activation energy.
Prudent Scholars, powered by Lupin Pharmaceuticals.